Today we are going to study about line integrals. For that we need to define integration f of xy dx and integration f of xy dy. So we need to take a function f which be defined at every point xy of the curve capital gamma, for which x equals to phi of t and y equals to psi of t, and also a is lesser equal to t lesser equal to b. So as usual we divide the interval ab into n finite parts, not necessarily all equal, by means of the arbitrary set of points t1, t2 till tn, where a equals to t0 less than t1 less than t2 less than, it goes on till tr minus 1 less than tr till tn minus 1 less than tn, which equals to b. Let p denote this partition and we set xi r equals to an arbitrary point in tr minus 1 tr within close brackets, and xr equals to phi of tr and yr equals to psi of tr. This is for r equals to 1 to n. So we define two types of line integrals as follows. The first one is integration f of xy dx, which equals to integration from x0 y0 to xn yn f of xy dx. This equals to limit partition p tends to 0 summation r equals to 1 to n f of phi of xi r and psi of xi r xr minus 1. This equals to limit summation r equals to 1 to n f of phi of xi r psi of xi r, and we substitute xr minus 1 into phi of tr minus phi of tr minus 1. Similarly we get integration f of xy dy. This equals to integration x0 y0 till xn yn f of xy dy. This equals to limit summation of r equals to 1 to n f of phi of xi r psi of xi r and yr minus 1, which gives us limit summation r equals to 1 to n f of phi of xi r psi of xi r, and we substituting we get psi of tr minus psi of tr minus 1, provided the defining limits exist. So from here we observe that x0 equals to phi of t0 equals to phi of a and y0 equals to psi of t0 equals to psi of a. xn equals to phi of tn equals to phi of b, and yn equals to psi of tn equals to psi of b. Heading on to the sufficient condition for the existence of the integral. If number 1, capital gamma be a regular curve, and number 2, f be continuous on capital gamma, then both integration f of xy dx and integration f of xy dy exist. So how do we observe this? We see that the first hypothesis may be altered in a variety of ways. Thus, if f be continuous on gamma, phi and psi be continuous, and differentiable in a lesser equal to t lesser equal to b. Both integration f of xy dx and integration f of xy dy exist, and by the mean value theorem we may come to the conclusion that integration f of xy dx equals to integration from a to b f of phi of t psi of t and dt. This equals to integration a to b f of phi of t psi of t d phi t. Okay, and similarly this integration f of xy dy equals to integration a to b f of phi of t psi of t d psi t. We mark this as 1 and this as 2. So we shall apply these two results 1 and 2 in evaluating line integrals. Again, the first hypothesis may be altered like this, that if the curve gamma be monotone in the sense that phi and psi are both monotone in a lesser equal to x lesser equal to b. And in addition to this, if phi of t equals to t and psi becomes continuous, then integration f of xy dx equals to integration a to b f of x psi of x dx. So we get this result. We mark this as 3. Another observation is that we may deduce some properties of line integrals. Here are some of these. Number 1 is if f and g are integrable on gamma, then f plus minus g are also integrable on gamma. And integration over gamma f plus minus g dx equals to integration over gamma f of dx plus minus integration over gamma g dx. Number 2 is that if an arc AB is composed of two arcs, that is AC and CB, then we may write that integration over AB arc f of dx equals to integration over arc AC f dx plus integration over arc CB f dx. So we need to clarify all these assertions with the help of some examples, and they are as follows. So in the first example, we see that we need to evaluate integration x plus y dx. If gamma be the two line segments y equals to 0, where 0 is less or equal to x less or equal to 1, and x equals to 0, where 0 is less or equal to y less or equal to 1. So how do we solve this? Here the integration is along two broken lines, which is AO from 1 0 to 0 0, which is this one, and OB, which is from 0 0 to 0 1. So using the given figure, we can write that integration x plus y dx equals to integration along the curve AO x plus y dx plus integration along the curve OB x plus y dx, which equals to integration 1 to 0 x plus 0 dx plus 0, which gives us minus half. So why do we write this 0, the second part? Since integration along the curve OB x plus y dx equals to 0, as in this case x equals to 0, whereby we get that dx equals to 0, hence the 0. For the same figure, if we need to evaluate, which is question number 2, if we need to evaluate integration x plus y dx plus x minus y dy over gamma, we get that integration x plus y dx plus x minus y dy equals to integration 1 to 0 x dx minus integration 0 to 1 y dy, which gives us minus 1. So in this way we need to study the line integrals.